Hedy Lamarr and George Amthale invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1 kilometer long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incremented in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent.
Workshop now, and thanks everyone to join this workshop. It's funded by the Charles Park, and then this is a workshop about information theory for a large language model. And our first talk will be the Professor Yue.
Right. And I would like to thank the organizers for organizing the workshop and for inviting me here. So I'm going to share some of our recent work on understanding ILVR, which is a very popular algorithm for training reasoning models. Let me see. So this is actually based on a paper that will be presenting next week at ICML. This is a paper led by two brilliant students, Yu Huang from UPenn, advised by Yu Ting and Yu Xin, and Zixin at CMU, advised by me and Artie, and this is also in collaboration with Professor Yingbin Liang, sitting in the audience, that she'll be giving the next talk. So large language models, I'm sure everyone are very familiar with it now, probably are using it every day. At the essence, this is essentially a next word predictor. So for example, here I show an example where you ask the model what reinforcement learning is, and the model is generating the answer word by word. So every time the output of the large language model can be viewed as a probability distribution of what the next possible word should be. And in this case, it predicts the most likely next word should be agent, and it basically produces it and then repeats the process. So this has found a lot of applications in NLP, translation, Q&A, summarization, and so on. But it also has been used for a lot of other applications, like reasoning, coding, and so on, as I'll talk about a little bit later. Beneath the large language model, transformer is a main architecture that is the backbone. Since the introduction of the attention mechanism back in 2017, 2018-ish, this has rapidly has been growing a lot, sort of boosting this new wave of AI. So this is actually at the bottom is a citation number for this paper that I updated a few days ago. As you can see, this has been cited by more than 260,000 times. So you can see just within a couple years, it has been growing a lot. So what is this transformer architecture? I'm not going to give you a full view from a practitioner's point of view, but maybe just a high-level abstraction that I think will be useful from a statistician's perspective. So the way I typically think about this kind of model is this is the so-called sequence-to-sequence model. So namely, you have a sequence, right? So for example, you have that sentence I showed at the beginning, and you can embed this sequence into some two-dimensional data matrix structure. So along the x dimensions, these are what we call the tokens. For simplicity, you can think of each of the token maybe just as a word, right? So you have a sentence, then you have a word-by-word representation of that sequence, and each word will be mapped to a high-dimensional feature embedding that gives you the second dimension of this data matrix, right? So the sentence will give you this kind of data block. And you pass this through the transformer. The transformer will do some manipulations and map you to another block, right? So again, token times the feature. What is inside the transformer is basically a concatenation of these transformer blocks. Probably you're very familiar with what a deep neural network is, which is just a concatenation of neural network layers. But here, this transformer blocks is a little bit special. It actually has two things. It has an attention mechanism followed by MLP. So MLP is what we all know from deep learning. This is what you apply along the feature dimension. So what it does is it's trying to figure out what is the best way to represent your data, right? So it tries to map the data, manipulate things in the feature dimension. But the special thing that is new for transformers is this attention mechanism. So what this attention tries to do, it looks across the token dimension. So this can be either a temporal dimension, spatial dimension. It tries to look across the associations among the tokens, figuring out which token is the most important, most associated or related to other tokens in this token dimension. And we'll compute some sort of like a correlation structure, attention structure. Okay. So that's sort of what this basic transformer block does. And you'll be repeating this over many, many transformer blocks, right? So then you get some sort of the deep structure at the end of the day. I hope this is clear. At least this is sort of abstraction that I think is useful when you think about what it does. For most of the time in the talk, I'll be just focusing on thinking about transformers with a single transformer block and doing some theory on top. But as you can imagine, if you have a deep structure, essentially, you'll be just repeating this process and refining it over many layers. So you can still build some high-level intuition, even with deeper structures. All right, so you have this basic sequence-to-sequence mapping. How do you do decoder-only or autoregressive generation? Very simple. You just take the last column of your output, and that will be your next word prediction. And then you append your prediction back to the input. So now your input is one word longer, but it's still a block. And you pass this through again, this transformer. It maps to another block that is a little bit longer, and then you repeat this process. So as you recursively apply this autoregressive mechanism, you can produce responses from your model longer and longer, right? And because of this capability, you can imagine something like chain of thought. So originally, chain of thought is proposed by Google DeepMind as a way for prompting the model to answer questions with higher reliability, higher accuracy. So the way this works is that let's say you ask the model to answer some math problem. if you ask the model to directly give you the answer, oftentimes the model fails. But if you just use a magic word, say, don't rush your answer. Try to think step by step before you answer me. And the model will actually structure its answer in this kind of structure that before it produces the final answer, it will try to give you some rationale that it uses to come to the answer. And all of a sudden, the model has much, much better capabilities in answering, especially reasoning type of questions like math questions. And if you can elicit this kind of chain of thought capabilities by prompting, why don't you try to train it directly, right? Try to train the model to natively has this kind of chain of thought capabilities. So this leads to actually this kind of reasoning models. First proposed by OpenAI back in the 2024, the model so-called O1 model. They didn't tell us what kind of formula or recipes they used to train the model. They simply say they trained this model using reinforcement learning. But they show this kind of pictures where if you look at the y-axis, these are sort of the compute time you use. So maybe look at the right-hand side, which is the x-axis is the test time compute. So intuitively, this is just the length of the answer you are getting. So if you allow the model to think longer, to produce longer and longer outputs, the performance of the model on all sorts of benchmarks, math, coding, and so on, all of a sudden scales up as you allow the model to think longer. So this is the so-called test time scaling, namely the capability of these models improves as you give it more time to think. So OpenAI doesn't tell us how this is being done, but DeepSeek actually tells us a little bit. So in early 2025, DeepSeek released this model called R1, and at the same time, they released this recipe called RLVR, so reinforcement learning with verified reward. So the idea is that if you're going to use reinforcement learning to train this model, but instead of trying to get some sort of train some sort of value network, you are only going to train the model based on some sort of terminal rewards. They're only going to look at if the final answer is correct or not, plus some kind of format sanity check. And this actually leads to a huge wave of research on RLVR and many sort of the follow-up reasoning models being trained from the open world because they actually have an open source model compared to the closed source model in the previous slide. But for this talk, the central question is, how does this actually work, right? Especially think about if you have a very, very difficult problem, you have to have a really long reasoning time. How can you actually train out RLVR so that it can actually solve a problem that is harder than it actually seen during training? All right, so with this in mind, I'm going to actually show a little bit of what we've done. Again, this is not trying to answer this in entirety, but maybe just some early steps about how we think we can maybe model this kind of problems. And the benchmark problem we are going to use is this so-called state tracking problem. So this is like a finite state machine-ish kind of model where you have, you're going to give the model initial state, and you are going to define a sequence of actions. So the agent will be hopping around different states based on the action you prescribe along this sequence. So this is a very naturally a chain of thought type of problem if you think about it, right? Because it will require some sort of sequential reasoning, some sort of step-by-step reasoning about how you actually track the dynamics of these variables. So we're going to use this as sort of a baseline problem to study. Mathematically, more formally, we are going to assume we have a group, say a group G, and this will be acting on a finite value set. So you start with some initial value, and you first apply some action, say G1, that maps it to Y1, and then G to Y2, and so on. So this naturally specifies a sequence where each step is specified by applying the corresponding action G. And the chain sort problem is simple. It's just that given the initial value, right, I tell you what y0 is, and I tell you the sequence of actions. Your job is to figure out what is the final value. Okay. What are some examples of this? Let's consider one simple example that is just modular sum. Right? So I have this sequence of equations that specifies how you get the next y based on the previous y and sort of this modular sum operation. And I give you the basic initial value. So you can find the final value essentially by applying this chain operation. So at each step, there is a group operation G. There is a previous value you need to know so that you can apply this reasoning at each step. Okay? So this is sort of the problem I want to study. But how do I actually map this to a format that the transformer can actually recognize? So again, as sort of some first step in theoretical studies, we have to make some manipulations. And this looks a little bit more complex, but let me just try to highlight a few of the key points. You don't have to maybe recognize or remember everything on the slide. But the high-level structure that we are going to inject in the reasoning data format is, again, you are going to have a prompt, right? So the prompt is like you tell the model what are these group operations. You tell the model what are these equations, right? And we have an answer clause. This is what the model needs to produce when to try to do this COT reasoning. We are going to give the initial value y0. The goal of the model is simply to predict all the intermediate values from y1 to yl. But in LVR, we only care about, or the environment only will evaluate whether your final answer is correct or not. You are not going to get any intermediate supervision for the intermediate results. Okay? So you can imagine if you have a shorter reasoning length, so L is small, this will be relatively easy. Right? But if you have a larger L where you have to do many, many intermediate steps, the problem will become much, much harder. To make the problem a little bit more tractable, so the way we formulate this is we're actually going to have a bunch of what we call position vectors. So you can see all these xp and xa's are position vectors. They are given in both the prompt and in the answer, and they have a correspondence specified by a permutation. So intuitively, you can imagine this is just like shuffling the equations in your prompt, right? So the model a priori do not know at what time it should be using which equation it needs to learn. Finally, we are going to embed all these group operations and the values as orthonormal vectors. So the transformer don't see them as the modular sum equations as you see in the previous slide, but see them as orthonormal vectors. In this talk, we're now training these embeddings. We're assuming these are given. Well, in reality, these things are also being trained. So the only thing we need to train essentially is training some sort of transformer parameters so that it can recover this permutation structure. But I'm speaking a little bit ahead of myself. But bottom line is, how does the transformer actually reason these things sequentially? What is a transformer structure? As I mentioned, we're going to just use a one-layer transformer architecture that has an attention block and an MLP block. So you have your sequence data, you have the prompt, you have maybe the first entry in your answer, that is your initial value, and that will be passed through the attention first, and then passed through the MLP. And the way we are going to think about the transformer is going to think about this as a policy. Why we can think of it as a policy? Because as I mentioned, the output of the transformer is basically a probability distribution over the next token. And in this case, it's also a probability distribution over the next possible value of y. So by giving all the previous things, that the model has, and calculate a probability distribution over the next y, and pick the largest one as a possible output. Okay. And we are going to apply reasoning recursively over this two-layer structure. So at each step, it's basically applying the same mechanism. So namely, at each step, we are trying to predict what the next value YL should be based on the current value YL minus 1 and the group action GL. So what attention will do is will function as a retrieval operation. So attention will look through the context and figuring out what is the correct GL from the context I should be using for my next step. Okay. Once attention figure out what the correct GL is, then the MLP essentially will be executing the group operation by applying GL on top of your current value YL minus 1, and map this to this function form. Roughly speaking, we understand how MLP works from the deep learning literature, because this is basically trying to learn a large neural network that can map high-dimensional vectors to your desired value. The thing that needs more research is really trying to understand this attention mechanism. So just a little bit more mapping from Y to Y prime, there is actually a unique G that maps this Y to Y prime. So this makes the problem just a little bit simpler. And we are also assuming this sort of asymptotic regime, so that the longest length, when you think of a long horizon plan, when you think of a long horizon planning is roughly speaking is the cardinality of your variable x. All right. So how do we train these models? We are going to use this kind of IOVR objective functions. So you only have reward for checking the final answer, and only when the final answer y hat agrees with y, you get a reward. So this is a rather standard IO objective function. For the training, for the parameters in the transformer, we are assuming we fix the MLP structure. So in other words, we assume the MLP is already been pre-trained to execute the atomic scale of the group actions. This may seem strong, but we actually have shown this in one of our previous papers. So the only thing we are going to train is attention mechanism, captured by this attention matrix Q. And we are going to apply just simple policy gradient updates on top. So this is just the standard policy gradient formulas. For the pre-trained atomic scale about the MLP part, let me just say one word. So we take this result from our previous paper about sort of the structure of the weight matrices in your MLP needs to satisfy. At the end of the day, there is only one important parameter, this CB parameter. This is a constant. Roughly speaking, this controls how accurate your atomic scale is. And this parameter will actually also pop up in our generalization analysis for ROVR. But in this talk, we are now training W. We are assuming this has been already pre-trained. All right, so now let me start to give you a little bit of the results. So the first result is just thinking about the training dynamic of the model, starting from with a fixed horizon L. So interestingly, what we found is that IL can actually already succeed for short horizon reasoning. Namely, if your reasoning length is smaller than that key parameter CB, then with sufficient training length, we can actually guarantee success of IL training. So your objective function will converge to 1. But on the other end, if the training length is slightly larger than, say, 2 times CB, then the gradient actually is exponentially small. So namely, with a single lens training, it's very hard to train for long horizon reasoning due to this kind of flat training dynamic. So you have very bad optimization landscape to make progress. So what do we do then? So actually, this is just an example to verify the result, right? So you see that at lens 5, the training actually succeeds very quickly, but for longer lens, there is no progress. So L learns short lens, but it doesn't succeed with long lens. So how do we actually make progress for longer lens? It turns out that you can actually try to train with a slightly different data recipe. So the way this works is, let's say you don't just train for one single lens, but a mixture of different lenses. And let's say I can schedule different lenses with some ratio R that I call the difficulty ratio. So this is an illustration that you have different lengths of the data, but you're going to train the model by just uniformly drawn from this mixture of data. So same objective, but the data is different. So let's look at what happens now. Things actually can look quite different. So if the ratio R is small, so that you have a smoother difficulty spectrum, similar to the previous example, but now we see that not only lens L equals 5 succeeds, the longer lens at 15 and 45 also succeed fairly fast, relatively speaking, to the lens 5 case. On the other end, if you have a higher difficulty ratio, say 7, then you actually do not observe any success for the longer lens 35, even though lens 5 still succeeds very quickly, right? So while on the left, you see that even with lens 45, it already succeeds. So this seems to be suggesting how RLVR can generalize differently when you have a different data mixture, right? Notice that here the reasoning structure actually are shared across different lens. So the way this being generalized across the horizon is actually driven by this implicit curriculum. So theoretically, what we've shown is essentially a more rigorous version of the empirical phenomenon you see in the previous slide. So because of time, I will not get into too much of the details, but if basically the result says that if the difficulty ratio is large, then there will be a long plateau before you can show success for the next lens. But as long as the difficulty ratio is small, then you can actually control this propagation so that the next lens will also succeed reasonably fast. Finally, there is a phase transition phenomenon which says that essentially the time from you see just a visible success to almost a perfect mastery will happen in a short duration. So you always see this kind of sharp transitions. All right. So this is, again, an illustration of sort of intuitively what happens. This is not a rigorous drawing. But what this is trying to show is that when you think about the learning signals that you get from a fixed lens, it goes through this kind of cycles. So the learning signal actually first grows, but once it gets closer to mastery, it actually starts to decay. So what happens when you have this kind of patterns for different lenses is that if the two lenses are widely separated, like in the first picture, then there is really no information borrowing or relaying from the easier case to the harder case. And what you see in the final learning is some kind of staircase picture, that there will be long plateau between the success of each phase. But on the other end, if the two lenses are not too far away, then you can imagine actually there's some learning signal that the shorter lens can help learning of the longer lens. So you actually get this kind of relay picture, like in the bottom one, and you will see much faster learning overall for the entire spectrum. So this, at the end, what this really tells us is RLVR is really the most efficient at this so-called agile competence, so that the model can leverage what it learned from the shorter horizon problem for learning the longer horizon problems. All right, so I think I'm running out of time, so I will skip some of the theoretical characterizations. But if you're interested, you can look at our paper for some more details. We do actually introduce some, I think, interesting new tools, which is this kind of Fourier analysis on groups so that we can handle this kind of compositional reasoning structures on this kind of step-by-step reasoning tasks. So again, because of time, I will now talk about the details. All right. So let me just quickly wrap up. There are a couple messages I want to highlight here. So the first is I think this is probably the first end-to-end learning dynamic analysis for this kind of outcome-based IL with transformer-based policies. Interestingly, I think this sort of shows that with ILVR, even you do not specify the curriculum a priori, the learning dynamic will implicitly track the curriculum from the data. So we'll actually learn the easier task first and gradually learn the harder task. And you want to be able to sort of carefully schedule the difficulty levels in your data to facilitate learning. So on the technical side, we introduced some new Fourier analysis tools that might be useful for study other problems as well. All right, so with this, I will conclude. If you are interested, you can find the paper on arXiv or on my webpage. So thank you so much for your time. I'll be happy to answer any questions you have.
Thank you very much, Professor Chi. So in the interest of time, we can probably take one question. Yes. Oh, sorry, no. That was a question. So maybe I can ask one question. So you talked about grouping, which is a very important phenomenon in pre-training. I saw that there are some results in pre-training that grouping really helped the model to learn what's going on. But in your research, you seem to say that pre-training, the grouping is not as important as relaying.
No, so it's also important. So what we are showing here is essentially the dynamics, how the reasoning from the shorter length problem generalized to the longer length problem. If the difficulty level between the two cases are too large, then the model will take a long time before you can pick up the signal from the longer length problem. So that will cause some long plateau. So the message here for the relaying case is that in your data mix, you probably want to mix different difficulty levels of data. That the data recipe is really important. Yes.
Okay. Thank you very much.
Thank you so much.
Yeah. So next, we welcome our next speaker, Dr. Yingbin Liang. Dr. Yingbin Liang is currently a professor at the Department of Electrical and Computer Engineering at the Ohio State University and a core faculty of the Ohio State Translational Data Analytics Institute. She also serves as the deputy director of the NSF AI Edge Institute and the co-lead for foundational AI pillar of OSU AI X Hub. Dr. Liang received a PhD degree in electrical engineering from University of Illinois at Urbana-Champaign in 2005 and served on the faculty of University of Hawaii and Syracuse University before she joined OSU. Dr. Liang's research lies at the intersection of machine learning, large-scale optimization, statistical signal processing, information theory, and wireless networks, with their growing applications to other scientific domains. She received the National Science Foundation Korea Award and the State of Hawaii Governor Innovation Award in 2009. She also received the EuroCIP Best Paper Award in 2014. She is currently an Information Theory Society Distinguished Lecturer from 2026 to 2027. Dr. Liang is an IEEE Fellow, so let's welcome Dr. Liang.
Thank you so much for the nice introduction. Yeah, I also want to thank the organizers for organizing this very exciting workshop and for inviting me here to give the talk. I'm very excited to share our recent studies on diffusion model. So let's give it a couple of minutes for the slides to come up. Main, M-A-I-N, main. Okay. Yeah, as you can see from the title, I'm going to talk about our studies on diffusion models. So here is a brief outline. I'm going to start with the introduction and then talk about our studies on three work recently. And finally, I'll conclude with comments on the future directions. So from a general context, generative modeling, the goal is to learn underlying distribution of data so that later on we can generate new samples that look like training data. So a traditional approach does this by fitting a parametric distribution and then sample from it. However, such approach encounters difficulties when data distribution is high-dimensional and complex. So this motivates the modern generative model approaches, which avoid fitting the distribution, but train a neural network to capture fine-grained structure. So in the past decade, we have seen generative modeling has evolved over several milestones, starting from the variational autoencoder and GANs to autoregressive approaches. And very recently, we have all witnessed the tremendous success of diffusion models for generating high-quality videos, audio, and images, and so on. So there are two types of diffusion models, and for both of them, they contain two processes. So in the forward process, we typically start from a clean image and then gradually add noise. So in the continuous diffusion model, we typically add Gaussian noise in the continuous space until we fully corrupt the image. And then in the reverse process, we train a model to denoise step by step until we recover the clean image. So in this way, model can learn how to go from the pure noise to a clean image. So such a continuous diffusion models have been very successful in generating images, videos, audios, and so on. And in parallel, discrete diffusion models have also been proposed to produce samples in the discrete space, such as language, molecules, music notes, or codes. So here, adding noise in the forward process becomes changing the states from one to another. For example, in the text data, what we do is to basically change these words continuously until we go to a stationary state. And in the end, the text will look very differently from the original text, or even doesn't carry any physical meaning. So discrete diffusion has witnessed successful applications, especially in the cases where the samples naturally lie in the discrete space. And from the research community, there has been a rapidly growing interest on discrete diffusion models. This figure actually shows the number of publications on discrete diffusions over the past few years. Just a little bit setup for the discrete diffusion. So we typically use a state to represent a sequence of tokens, let's see D tokens. For example, in the text data, the sample can be diffusion models can generate novel videos, which contains 6 tokens where each word is chosen from the dictionary set. So such a discrete diffusion models can be modeled or captured by continuous time Markov chain, which is typically specified by the initial distribution and transition rate matrix. In particular, suppose over a certain time duration delta t, then from one state x to another state y, the probability can contain one possibility of staying the same, or transitions from x to a different y, captured by these 2 terms. In particular, the first order term has a rate matrix, which is typically positive if x is not equal to y. And this summation to 0 basically preserves the probability during the entire process. So there are typically 2 ways to choose such a transition rate matrix. So one way is to choose the uniform rate, meaning that at each time, the word will change to any other word in the dictionary with equal probability. So in this case, the final stationary distribution will have all these tokens distributed uniformly over the dictionary set. And in the second case, we introduce a mask. And then at each time, the word either stays the same or changes to the mask state. So in the end, the stationary state will basically contain all masked state. So the reverse process can also be expressed in the similar way, where the reverse matrix has been shown to equal to the product of the forward rate matrix, multiply these ratios between the marginal distribution of y and x. And we typically define such a score function to be the ratio. And once we learn such a score function, then we can generate samples based on such a reverse process. So next, let me talk about our first work. So although the diffusion models have been quite successful in practice, its practical employment encounters true difficulty. So it has been demonstrated that diffusion models require many steps to achieve desired generation quality. So this basically means we have a very slow generation and delayed result, limiting its applications in the real-time and interactive domains. And it also causes high energy consumption and computational cost. To just give you some concrete sense about this, a 4-second diffusion video can use about as much energy as a full charged smartphone. So this also has been reflected in the theoretical results so far. So in this table, so several studies have characterized the number of denoising steps needed for uniform rate diffusion models to achieve certain required accuracy. So if we look at all these results, they all have the dependence on this epsilon. Epsilon is a required target accuracy. So they all depend on 1 over epsilon in the polynomial 1 over epsilon. So, for example, if we set epsilon to be 10 to the -3, which is a reasonable accuracy requirement, then 1 over epsilon becomes 1,000. So from all these results, it all suggests that there is a large number of denoising steps needed. And our question now is, can we actually accelerate such samplers to achieve faster rate? For example, log 1 over epsilon. If this is indeed true, then for the same epsilon, log 1 over epsilon will just mean 7 steps for the denoising, which certainly is much faster. So to achieve this, in our study, we proposed a Gibbs accelerated discrete diffusion sampler. So the idea is the following. So if you look at the outer loop denoising steps, we'll basically use the conventional denoising sampler. However, for each step, we introduce an inner loop called Gibbs corrector, which will bring the initial state further close to the final target. So the hope is by doing this, we'll need a smaller number of denoising steps overall. To just give you a sense about what the Gibbs sampling is, so we typically start from an initial state, and at each step, we sample one token with a certain weight and update the state for that token based on posterior distribution given all other tokens' state. So such a Gibbs sampling will definitely help. However, typically, we require Gibbs sampling to be fast so that it can bring in advantage. To do this, we require the following two conditions. So the first, we need to have access to the posterior likelihood distribution. And second, we need a good initialization point, which is also the warm stat. So if you think about the diffusion model, in fact, in the denoising steps, typically, we always design the distributions for adjacent steps to be very close. So this makes the warm stat as a natural thing in the diffusion model that's satisfied. So basically, we need to check how do we get this posterior likelihood. And somewhat remarkably, in the diffusion models, we can also make an easy estimator for this. So just to remind you, in the diffusion model, we define the score function to be this ratio. And in the inference time, we typically assume such a score has been well pre-trained. So then, to get the posterior likelihood, we can rewrite it in a different form so that you quickly realize this is simply the score function evaluated at these two values. So this allows me to simply plug in the pre-trained score function here so that we also get a good posterior likelihood estimator. So our theorem shows that if we want to achieve the close distance between the target and the outcome generated by my sampler to be within the square root of epsilon, then I just need this number of steps, which include both the inner and outer loop steps. And here, rho star basically associated with the general distribution of the samples. And the second term in the numerator is also independent of epsilon. So basically, only the first term dominates the performance, and as you can recognize immediately, it's basically log 1 over epsilon as we need. So this result indeed tells us that such an accelerated sampler indeed achieves Pauli log 1 over epsilon rather than in the previous result, which has only Pauli 1 over epsilon. So to just give you a sense about how we get the benefit, so the top part of the figure shows the conventional diffusion model, so the performance of conventional diffusion model that needs Pauli 1 over epsilon steps. So the bottom one, if you look at it, at each step, we have additional cost by using this inner Gibbs sampling, which is log 1 over epsilon. However, this additional cost is indeed worthwhile because it makes the distribution closer to the target so that the overall denoising steps needed is also reduced to Pauli log 1 over epsilon. So overall, in total, if we take a product, we still get poly log 1 over epsilon. So our numerical result indeed verifies our theoretical results. As you can see that our sampler is much faster than the conventional sampler and recently proposed accelerated ones. And this one shows the experiment on a real data. And as you can see that compared with all these baselines, our sampler for the same number of denoising steps, we achieve much less perplexity and uses much shorter time. All right, so let me quickly get to the masked diffusion model and talk about our result here. So as I just introduced, for the masked diffusion model, we have a mask state introduced, and then at each step, the word changes either to the mask state or stays the same. So masked diffusion model has been quite successful, especially for those applications associated with language. For example, produce documents from scratch or translate text from one language to another. So the basic advantage comes from it's actually generating these tokens based on both directions, not just limited from the left to right generation order. So here, our research goal is to characterize, again, what is the fundamental step, necessary denoising steps needed for these masked diffusion samplers to generate high-quality data. So next, I'll just briefly show you our recent result on this conventional Euler sampler. So it achieves the total variation between the target and the generated distribution bounded by such an upper bound. And in particular, if I want to achieve epsilon accuracy, I basically need ds divided by square root of epsilon steps. So d means the number of tokens, s is the cardinality set, size of the cardinality set. To see if this is indeed tight, we provide a lower bound that shows that there indeed exists a certain distribution such that to achieve the total variation less than square root of epsilon, the number of denoising steps needed is d divided by square root of epsilon. So this indeed shows that our characterization of the sample complexity is tight in d and epsilon. And next, for a very recently proposed sampler, which is called FHS, it actually uses the random steps for sampling to match the forward process. And not very surprisingly, the KL divergence between the target and the generated output is just bounded by the score estimation error. And our lower bound also shows that such a characterization is indeed tight. So which tell us that FHS, in fact, achieves the best theoretically characterized number of steps or the complexity of the denoisers. All right, so finally, let me get to the post-training of diffusion models. So typically, pre-trained diffusion models make a general purpose generator. However, in many applications, we actually require the output to satisfy certain user-specified requirements, such as human preference or some scientific properties. So this makes post-training important. Just to give you an example, suppose we want to generate a text to explain solar eclipse. So if I use a general purpose pre-trained sampler, it gives me such a text, which is technical and accurate, however, may not be easy to understand, for example, by children. Suppose we would like to generate something that can be easily understood by kids. So then I can pre-train the model so that it gives me a text that conveys the same meaning, but much easier to understand. For example, it says the moon moves in front of the sun so that the sun can look darker or even disappear for a short time. So how do we post-train the diffusion model? So reinforcement learning turns out to be a powerful approach. So basically, we can view the reverse denoising process as a Markov decision process. So the state will basically be the state in the denoising process, and the policy can be captured by the score function in the diffusion model, and the action can be viewed as the score introduced the drift from one state to the next. And such a MDP process will have a trajectory from the full noise state to the final clean image. Finally, the reward function can evaluate the quality of the final outcome. So here, let's just focus on the continuous time diffusion process, which can be expressed in such an OU expression. So here, X tau represents the noisy sample, and W tau represents the Brownian motion. And we have the drift term that gradually shrinks the signal towards zero, and the second term is injected noise. So such a forward process will correspond to a reverse process described in this form. As you can see that there is a parameter lambda that controls the stochasticity of this reverse sampling trajectory. So there are two regimes that we are interested. So the first one is an interpolation regime when lambda is between 0 to 1. So if lambda is 0, as you can see, this term will fully disappear. So the reverse process is basically deterministic. And if lambda equals 1, that's what we typically know as the DDPM algorithm, which is what sometimes we call it fully stochastic SDE. And when lambda is between these two values, we're basically interpolating between these two processes. And there's also another regime that's not rarely studied, but which turns out to be also interesting in our case. It's called extrapolation regime. That's when lambda is bigger than 1. So we have a more noise injected at each step. Then not surprisingly, we need to increase our drift term to compensate for that. So this basically means the process becomes more stochastic. So here we also define the score function to be the term over here in the drift term, and we also assume there is a pre-trained model that satisfies this absolute accuracy. So the post-training will basically want to shift this model in the pre-trained case towards maximizing the certain reward function. And we also add a regularizer term so that this post-trained model will not be too far away from the pre-trained model. There have been various post-training algorithms proposed in the past, which are basically quite successful in practice. However, in this study, the question we ask is from theoretical side. So we want to understand if PPO, which is the foundations of some of these algorithms, if such a PPO post-training algorithm will converge provably. And furthermore, what stochasticity parameter lambda, as I introduced before, is most favorable for the post-training. So here is our result. Let's just focus on the most important part. So basically, it shows that the average gradient norm is bounded by these two terms. First term captures the variance of the policy gradient estimator, and the second one captures the clipping error introduced by PPO algorithm. As we can see, both of these terms decays with 1 over square root of n. N is the number of iteration steps. So this indeed tells us PPO does converge in the rate of 1 over square root of n. That's the same as the typical SGD rate. And more importantly, both terms depend on this lambda over here. And you can easily recognize the second coefficient is simply the square of the first one. So let's just focus on the second one as a function of lambda. So basically, we want this f lambda to be as small as possible, meaning the convergence rate will be fast. So this figure plots a certain function of lambda for a certain parameters. As you can see here, there is a lambda star that achieves a minimal value for this f lambda, indicating that this will give us the fastest convergence. And more generally, we can show that as long as the step size beta is small enough, our optimal lambda star is always between 1 and 3. So what does this mean? So remember, we have an interpolation regime when lambda is between 0 to 1, which is the most popular regime that people use in practice. So as you can see here, as lambda is in 0 to 1, basically f lambda keep on decrease as lambda increases. So this tells us the DDPM when lambda equals 1 works the best in such a regime. Why is that? Because, so here, basically more stochasticity will get the benefit from the RL exploration. And furthermore, for the extrapolation regime, when lambda is bigger than 1, so in this case, we have larger lambda initially benefits the convergence, but later on, it will eventually hurt my convergence. So this basically tells us initially more stochasticity will still encourage the exploration in RL algorithm, but then later on, since we had more and more noise, it will eventually hurt the convergence. So this, for these two regimes, they basically tell us this stochasticity indeed controls the exploration and stability trade-off. So I think it will benefit by comparing the pre-training and post-training of these diffusion models. So in the pre-training, so our objective is to approximate data distribution accurately and efficiently. So it turns out the deterministic ODE from both the experimental and the theoretical result indicates that such a lambda equals 0 is often preferred because it reduces the sampling variance and enables the fast generation. However, in the post-training, the story becomes a little different because our goal here now is to move the samples towards high-reward regions. So a certain stochasticity will actually benefit this process because it makes us easier to escape from the low-reward regions and find what will be the best for the post-training. So our experiment also verifies our theoretical result. From this figure, you can see that as lambda increases from 0 to 1, then you get reward faster and faster. And furthermore, we plot the figure where how the reward depends on the values of lambda. And indeed, you can see that when lambda exists optimal lambda between 1 and 3 that maximizes the reward for a given steps. So finally, let me conclude very quickly. So we provide a new analytical approach for characterizing the number of denoising steps for diffusion models. And we also propose an accelerated uniform rate sampler that achieves a much faster rate. And for the post-training, we provide perhaps the first convergence guarantee for PPO. And our main insight is that the stochasticity parameter is important and critical for balancing between the exploration and the stability. This is, in fact, a quite open area and invite a lot of new contributions from the research community. So finally, I want to acknowledge all my collaborators for all these works. And thank you so much for the attention.
Thank you, Professor Liang, for the talk. We can ask questions now. So maybe I have one question first. You talked about post-training for diffusion models. So as far as I know, for transformers or language models, people post-train those models for a specific task using some specific data set. Is it the same for diffusion model? You train it for specific tasks?
Yeah, typically you do train it for specific tasks because then you have a specific reward function required for that task.
So the reward function is different from the pre-training reward?
Yeah, it's different.
Okay.
Depending on what you are interested in the downstream.
Thank you. Any other questions? So if not, let's thank the speakers again, Professor Chi and Professor Liang, for the
Thank you so much.
For the very inspiring talks. And since we are running over time, our panel will be canceled. So we'll come back at 4 for the oral presentations. Thank you.
有声音吗？
有。
看一下就。
afternoon session. So welcome to our next speaker, Joseph Ruan from the University of Toronto, who will give the presentation of multiple importance sampling for guided speculative inference.
Okay, thanks for coming. So today I'll be presenting our work on multiple importance sampling for guided speculative inference. So if that doesn't ring any bells, I'll be explaining what all that actually means soon. Right, so I think in the first part of this workshop there was a bit of discussion about test time scaling of LLMs. And so effectively, this work is focusing on the same sort of paradigm. So while LLMs have been made hugely successful by scaling the number of parameters, also at each step we'll choose the best one. So this is going to be focusing on the so-called best of n scaling, which is probably one of the simplest types that you can have. So how does the best of n sampling work in the most basic case, which is what we're going to build from here? So essentially, we need a process reward model, which is in practice another neural network or language model that will judge the quality of partial outputs. So then we run the model in a sequence of reasoning steps, and at each step, n candidate blocks of tokens are generated. So that would be each one representing one step. And then we run this reward model on all of them, and then simply select which one maximizes the reward. So although this seems sort of obvious, it's actually been shown in practice to be quite competitive and has also been analyzed, for example, in this paper from a theoretical point of view as well. So to visualize how it works, we have our prompt here, and then for the first thinking step, we generated these three responses. So here n is 3, right? And then it chooses this one and then adds it to the context and then continues on like this until it gets to the final answer. So one issue with this is that it relies heavily on this reward model being able to distinguish what's a good output and what's a bad one. But however, potentially the reward model itself could have some flaws in it, which can result in something called the reward hacking, where basically because we're picking whichever one the reward model thought is better, that response might sort of exploit a flaw in the reward model instead of actually being a good response from the perspective of actually answering the question. So one recent approach by Verdun in last year introduced the KL regularized reward optimization in the setting of best of n, where instead of just picking the maximum reward, it optimizes this objective function where we have included this term to try to ensure that the output distribution, pi tilde, is not too far away from the original one, and the beta controls the strength of that. So it can be easily shown that the closed form solution for this is given by this tilted distribution here. However, we cannot directly sample from this in the context of a language model due to the normalizing constant being intractable. So therefore, what was proposed in the soft best of n paper was to use importance sampling, where we generate the n samples and then compute these weights proportional to this tilted reward here. And then we resample the winning one based on those rewards. So for example, what it could do is it could, like, this is just one example where we had a quadratic reward, I believe, and then this is how it would reshape the probability density from pi to the tilted one there, right? Okay, so the next step was proposed also recently, is called a guided speculative inference. So if maybe you're familiar with speculative decoding, the idea being that a smaller language model is used to sort of guess what the original language model is going to output, and then if it guesses correctly, then it will accelerate the process. So here, what the new thing introduced in this speculative method is that instead of drawing the samples from, our original model, pi, they're now drawn from this small model, pi sub s, and then by rearranging the equations, the new reward weight should become this. So the new term is this log probability ratio between the original model that we actually want to approximate and then the small one. So the flow now looks like this. We draw the samples from the small model, evaluate both the reward function R and also the probability under the large model pi sub b, and then we use these importance weights to select the sample we want. Okay, so finally, I'll get to what we have added to this. So previously, that was importance sampling, right? So we had the importance sampling weights, and then we used them to resample from a pool of samples. However, we know from importance sampling that to actually become a good approximation to the distribution of interest, it must satisfy this. So the support of the draft model would need to cover the entire support of the large model. And while it's hard to actually picture what the support of the probability distribution of a language model over a paragraph would be, if you think about just normal distributions, when we had before, when we had before this one with a quadratic reward, we can see that perhaps the small model might only cover one part of it. So the idea of multiple importance sampling is by using non-identically distributed proposals, we can relax it so that we only need the union of the supports of those proposals to cover the large model here. So now we add two models, small model 1 and small model 2, and the union of them covers the reward tilted one and therefore also the large model itself. So that's sort of the motivation of why we would introduce several small models. And in practice, they might be like fine-tuned on different things. For example, like one might be a coding model, one might be a math model or something like that, or they could potentially have different architectures as well. So I just wanted to mention where it comes from. So one nice example of where the multiple importance sampling was very useful was in computer graphics, where the distribution, there were two distributions, right? One was taking into account the reflection of the surface, and the other one taking into account the position of the light source. So in this setting, it was very successful. You can see that if we only consider the surface distribution, then when the light source is very small, it fails to find the light, like on this side. However, if you used only the light distribution for the sampling, then where the light becomes more clear over here, the reflection becomes worse. So then by combining them, you get like the perfect image. So we thought maybe this could also be applied to a language model, but we'll see whether it actually works or not. All right, so to apply the multiple importance sampling to the guided speculative inference framework that I showed before, we just substitute in, instead of having just the small model's likelihood, we put in a multiple importance sampling weight. So I haven't actually shown what form this takes because it can take any number of forms, but there's like some canonical ones. So the new framework becomes that we draw the samples as before. Again, the inputs into the algorithm will be the rewards and the likelihood under the large model, so that doesn't change. But now we'll put that into some function and then get out a new weight that will be used for the resampling step. And then again, we'll pick one of them and then append that to the context. Okay, so to actually choose what these weights will be, there's some criteria here that should be followed. So basically, the first one is saying that whenever the support of the density that we're trying to approximate is greater than 0, then the importance sampling weights, the multiple importance sampling weights need to sum to 1. And then the other thing that it says here is that if that proposal does not have any mass at that point, whereas the target does, then the multiple importance sampling weight should be 0. But even within these two requirements, there are multiple things that can be done. So the first one is most simply a uniform weight. Now that only actually satisfies these in certain circumstances, right? It doesn't always satisfy these two, but it's still commonly used. And the second one is called a balanced heuristic, which uses the denominator here has the mixture distribution of the different proposals. So in this paper here, they were called scheme N1 and N3, and those are like the most common ones, so we're going to consider them in more detail. So we can sort of repeat the arguments that were made in these two works. So that's the soft best of n and then the guided speculative inference. And then we'll see how they have counterparts for our multiple importance sampling. So basically, this is just saying that if we push through the scheme, we can bound the KL divergence from the optimal tilted distribution, and then this pi tilde is the actual output of the algorithm. So we have these bounds. So for the guided speculative inference, the thing is that it's the chi-squared divergence between the draft model and the large model that shows up in the bound. So it's showing that essentially if they're far apart, then we'll have a loose bound on actually how well it approximates the optimal reward tilted output. So to prove similar stuff, I'll just go through this quickly. So first we have a bound on the probability mass that arises after doing the multiple importance sampling. And then after that, we can show the following results. So in general, we have this form for the KL divergence. And then again, the chi-squared divergence shows up, but depending on whether we use scheme 1 or 3, it shows up in a different way. So for this one, this is the mean chi-squared divergence between the target and then all of the proposals, and then this one involves the mixture distribution. And then again with that, if we go one step further, we can actually bound the reward that is expected to be obtained under these two schemes. That's just a small extension to the KL bound that I showed before. So as I mentioned when I showed the bounds initially, these divergences are the operational terms that will determine how tight the bounds actually are. So for the original guided speculative inference, we simply had the divergence between the large model and the draft model. For scheme N1, we sum up all of them and then take the average. Then for scheme 3, we have the mixture distribution, and then we take the divergence between the mixture distribution and the target distribution. So because it's convex, then we know that, at least in terms of the bound, scheme N3 will do better than scheme N1, always. We can say something even better, that actually the scheme N3, the balance heuristic, is the best one in terms of that bound among all of the possible schemes that satisfy those two requirements that I showed earlier. And if it doesn't satisfy the requirements, we consider it invalid because it would not approximate it at all, right? So if you want to use the multiple importance sampling, then N3 is the correct one. I'll just mention before, though, it does have one issue with it, is that if we go back to the actual expression for the weights, it involves this, right? So we have to evaluate the likelihood under each of the small models instead of just the one that produced it. So that creates an extra overhead. But we'll see whether it's worth it. So here's some, to finish up, I'll show the experiments. So we use like reasoning data sets to test how good the performance is, and then we use this math model to produce the answers. And then the draft models are these three ones. So we have n equals 3, and then when we use the GSI, which only has one draft model, we just pick the math one. Now, given that these questions are like about math, we expect that this model will be the best draft model. So that will show up in the results soon. So in this table, we've measured the accuracy given n. So n is equal to the total number of samples that we take the best out of. And then among this, a third of them are from each of the different draft models. So it's a little bit hard to see a pattern, but essentially we can see that when n is small, the multiple importance sampling gets a better accuracy for the multiple choice questions. For the math questions, because this one is using the math model only, it does better. However, the other models don't drag down the performance too much, like it's only a tiny bit, right? So that sort of shows that despite using essentially only 1/3 the number of samples from the math model, the multiple importance sampling scheme can sort of prevent those bad answers from dragging down the performance. And then we also plot the tilted reward. So as you can see that the reward is sort of hard to see a pattern here, but they're all pretty much the same on this data set. However, for the more diverse multiple choice questions data set, we can see that it's consistently the multiple importance sampling is getting the best reward, although the gap is quite small. However, as we saw on the pass at n, you see the gap is decently larger when n is smaller. So I mentioned that it was computationally more expensive to run the N3 scheme, which is true. However, due to the way you can implement on the GPU, essentially many of the steps can be done in parallel if you have spare GPU resources. So the time increase is actually quite small if you implement it correctly. Especially as N is large, you can see they all take quite a long time, but none of them are particularly a lot slower than the other. All right, so just to wrap up, we introduced the multiple importance sampling in the context of speculative reasoning with a process reward model, and then it provides some theoretical guarantees on the divergence from the optimal tilted distribution. I mean, I'm not super happy with the experimental result like this. However, I believe that the theoretical framework offers the opportunity to perhaps try more complicated things that might, add a prior to maybe which draft model we should give the question to, or use an unequal split of N or stuff like that could be added in to try to improve these empirical performance. All right, and also we can try more complicated stuff rather than just answering math problems that might be more interesting. All right, so that's all, so thanks. I'm happy to answer any questions.
Okay, so any questions?
Yeah.
How much speed up speculation? I said in yours, how much speed up?
So I should have shown the speed up, but if you look at the guided speculative inference paper, we have pretty much a similar performance. So it depends on which model you use. However, it can be like, I'm trying to remember. I think it can be like 50% or something like this if you have a good data set, but in some cases it can actually become slower if you have like a bad draft model. Yeah. So it's quite variable, but in some settings it makes sense to use it.
Okay, any more questions? Okay, if no more questions, thanks again for your presentation. Yeah. Okay, let's welcome our next speaker, Ce Zheng from Pengcheng Lab, whose topic is SpecFed, Accelerating Federated LLM Inference with Speculative Decoding and Compressed Transmission.
Okay, everyone, thanks for still being here since it's the last lecture of this session. My name is Ce Zheng. I'm from Pengcheng Lab. I'm currently working as an assistant researcher. So the topic today is about SpecFed, Accelerating Federated LLM Inference with Speculative Decoding and the Compressed Transmission. By the way, it's quite reassuring that I just saw someone else is also working on speculative decoding, especially in information theory. There's not too much of work in terms of information theory, by the way. So this is about the table of contents today, and I would just first get the motivation of what is the federated LLM inference, and then I introduce the system model and how the speculative decoding can accelerate this federated LLM inference. And then we move to the compressed transmission, and then with the experience and takeaways. So now first is about the motivations. And so what is federated? In this part, I will just introduce what is federated inference and how it could be applied for LLM. So we just first let's look at the computer vision task, a very classic classification task that you got an image and you try to guess or make a decision on what class it falls into. So you have like one model, then the model will give you a probability distribution over the like 20 or 30 classes. Take this for example, is that you get an image, you ask what is the animal, it would be like llama, alpaca, or vicuna. The model one, you have one model which gives probability P1, and then you get another model which gives probability P2. And the federated inference in computer vision, what it does is that it takes the weighted sum of them both. For simplicity, I just use like the 1/2, and then you take the weighted sum or just average, and you get a new probability, which is P bar here, and then you make decisions on this probability P bar. And previous work has shown that this CV classification task can be improved by simply ensembling the classification results from different models. By ensembling, we mean aggregating probabilities, that is taking weighted sum. Okay, next, let's move to the very popular language model problem, that is text generation. For instance, you have like input questions and ask what kind of animals has these banana-shaped ears, and then your LLM model will try to guess from the and answer your questions. And what the LLM does is that they actually they generate a probability distribution, but very differently is that the probability distribution is not among like 20 or 30 classes. This is the probability is over a vocabulary. Depends on your tokenizer, the type of tokenizer. Maybe could be like 30 like 100,000 tokens, or maybe like 32,000 tokens. Maybe it's quite a very large vocabulary, but still it's a kind of distribution. And after get a distribution, again you sample a token from these distributions. This is how the LLM works. And then since it's so what I can say, what I want to say is that we can show that the text generation can still be viewed as a classification task. Since text generation can be viewed as a classification task, the LLM inference could also be improved by simply aggregating the outputs of multiple models. So this has been proved by the previous work. This is not my work, but it's very quite popular recently. Okay, so that's so much about like why federated inference can be applied for LLM. And then we move to our system model, which is federated LLM system. And then we'll bring the problem of autoregressive generation for slowing down the inference speed. And then we move to the speculative decoding introduction. So in our system, we have like we assume that we have n workers, each one of them deployed with an individual large language model. And for the generation, for instance, we have when we generate the teeth token, what they do is that each LLM generates a probability which got PTX, and then send its probability PTX to the aggregator. The aggregator could be deployed to a server or a peer worker, and then the aggregator does the aggregation. Here is just we take a weighted average just for simplicity, and then you get a new probabilities P bar, and then you sample a token XT from P bar, and then you send the token XT back to the worker, and with the newly generated token XT, it will generate the next token in this recursive way until you mate the token end of sequence or reach the maximum number of the token lengths of the task. The problem is that if you want to generate 100 tokens, what you do is that you need to run each of the LLMs for like 100 times. This will slow down your inference speed drastically. Why does this happen? This is because the quite specific nature of autoregressive decoding or autoregressive generation for LLM. That is, when you want to generate the second token, you need the first token as input. Take this for example. We assume that we have an input prompt or we call prefix, that is S1 to Sn, and then we want to, when we generate token, the first token x1 is that we first take S as input of the LLM, and then the LLM do the one forward pass, and generate the distribution Q1x, and then sample the x1 from the distribution Q1x, and then we use x1 as the input for the second token generation, and then again. So the generation of the next token requires the previous tokens as input. That's why it slows down the inference speed, which is also called the memory bound, probably in AI, but in speculative decoding, what they do is that they deploy a small language model, and the smaller language model generates the tokens in a much more, still in an autoregressive manner. But once it got like a bunch of tokens, and then it inputs, it sends the tokens to large language model as inputs, and the large language models takes all of them, the generate tokens and the prefix as input, and does just one forward pass and generates a bunch of probabilities, and then verifies these draft tokens generated from the SLM as small language models. By doing so, it could be accelerated the inference, because the runtime of small language models is usually several orders of magnitude shorter than that of large language models. By the way, for instance here, if we accept all of the tokens, as the LLM will generate a new tokens, which we call it a bonus token. But if we get a rejected, for instance, we have like X3 get rejected, and the LLM will like resample a new token from a resampling from adjusted distribution, and which we call X prime 3. And by doing so, we have like very strict mathematical proofs from the, I think it's Google's paper or DeepMind paper, I don't recall. The fast inference while speculative decoding, they have proved that in this way, the generate tokens follows the exactly same distribution from the LLM inference standalone. Okay, there's so much about speculative decoding. Now let's move to our system, SpecFed. So we still have like N workers, each one with individual large language models. And the difference is that we just deployed a small language model as a server and ask the server to generate the tokens in an autoregressive way. And after we get a bunch of the draft tokens, the server broadcasts its newly generated draft tokens to each of the workers. And then the worker, each of the worker will do the one forward pass using its own specific LLM. And they got a bunch of probability distributions. And each of the worker will transmit or upload their probability distributions to the server, and the server does the aggregation. By doing so, so each LLM only did one forward pass to get, like, in our case, it's 4 probability distributions for each of the, for the 4 tokens. But then there came a very unique, the severe communication bottleneck, because the probability distribution PTX is over a vocabulary size, or is over a vocabulary, and your vocabulary size could be very large. unlike the classic, because in civic classification, probably it could be like less than 100, but in text generation, it could be like 100,000 or even large, depending on your tokenizer. So to mitigate the communication bound problem, we choose to. This is actually a very naive idea. We just compress the probabilities. We're using a top K. That we choose the K most the greatest K probabilities and its corresponding token IDs, and then transmitted them. And then at the server side, we try to recover or reconstruct the distribution. So at the worker side, so each worker we try to do the top K truncation or top K compression, which denoted with KI. So, and then they send the top K its token IDs with KI and their probabilities to the server. And at the server side, the server try to recover it. What we do is that we just propose like two very naive recovery schemes. One is renormalized top K reconstructions. What does it mean is that we just renormalize over these top K tokens over here, and let the other untransmitted tokens, their probability to be 0. By doing so, we still make sure, this is just make sure that the sum of the probabilities goes to 1. And the second one is a residual mass redistribution, which means that we keep the top K token probabilities and then redistribute the remaining, or what we call residual mass, uniformly over the rest of the tokens, where V is the vocabulary size and Ki is top K, the probability tokens you kept. Okay, so this is about the theoretical analysis. We to show because when you do this, you get two newly distributions, right? Which is kind of distorted from the original one. So we want to show how distorted it is from the original one. So we propose we define a metric which we call aggregation bias, which is delta K. That is one norm of the distribution P bar K minus P bar. By the way, P bar is a weighted sum from the your LLMs of different LLMs, and PK is the one after weighted, not after compressed transmission, and of course with these two recovery schemes. And K is a vector, K1 to Kn. That means for first token, worker, you choose like top K1, and the nth worker choose top Kn. And then we give a very solid mathematical proof that the aggregation bias is upper bounded by 2 times epsilon K, where epsilon K is the weighted sum of the residual mass from each of the worker or each of the LLM model. So this theorem does provide a distribution level guarantee. That is our top K truncation. We have like a bounded, it's strictly bounded at the aggregation level. That is the weighted sum of the residual mass. And also we also introduced one that is exceptional rate variation. And by the way, this aggregation bias is trying to capture how much the aggregate distribution changes. The second one is exceptional rate variation. This one is to capture how much speculative verification behavior changes, because the acceptance rate is where alpha is the acceptance rate of the speculative decoding, and the acceptance rate is actually a metric that shows or decides how many draft tokens will be accepted during the verification case. And we show that the acceptance rate variation is also bounded by the weighted sum of the residual mass. So this provides a decoding efficiency guarantee because the perturbation of the acceptance behavior caused by compressed stretching is also bounded. Okay, then we move to our experience. This is a set of our experience. We choose like 2 models for LLM to mimic to simulate the heterogeneous federation. That is Llama 7B and Llama 13B. And for SLM, we have Llama 68M. And just for simplicity, we choose like equal equations to be 1/2. We actually, when we do a simulation, we found a very unique problems is that existing evaluations may not be a very good choice because existing evaluations either focus on task accuracy or similarity of the final output token. But this has like 2 limitations. The first limitation is that token sampling is random, quite random, which means an autoregressive decoding propagates early randomness across layered steps, which means even you have like the exactly same model and you have the exactly same prefix, you run it 2 times, you probably get 2 different results. The second limitation is that the task accuracy or similarity can look correct while hiding token or distribution level bias from lossy inference, which means that you probably get a token that might be semantically right, but not very aligned with our final distribution. By final distribution, it means that the one we choose like without any compressed method. But still it achieves a good performance. But it will be hard for us to see how much the distortion will be from the original distribution. So what we do is we redesign the evaluation pipeline. We still run the federated inference without the compressed transmission that we call full federated inference. And then we reconstruct. Then we do the compression and reconstruct the distributions by applying these 2 recovery schemes, as I just mentioned, to get the distorted distribution. And then we compute the bias, and by bias we mean the distribution bias and the acceptance rate bias or acceptance rate variations, and then average over the steps and samples. So this is the result. And we find out one of the significant hyperparameters is the temperature, because when we're doing the softmax, when you choose the temperature to be 0, you probably get like just only one token with a probability equals to 0. And the temperature directly affects the residual mass, because you choose like temperature very, very low, high chances your residual mass will be very, very small. Even you choose like a K to be very large, but if you choose like temperature to be like 2 or even very large, you got a very dispersed probability distributions. And also we choose that K is same for all models, which means that for our model LLM model 1 or large language model 2, they're the same. And the next one is communication payload, which is co-over way. This is just to be like shown in very good shape, because by doing so we can like show it in percentage. And the figure 2 is the average aggregation bias under varying communication loads under different temperature. And the vocabulary size we choose to be 32,000. And we have like two kind of reconstruction methods. And this one is the weighted sum of the residual mass. It can be shown that these 2 reconstruction methods is bounded by the green one, which is weighted sum. So we should this one confirms our theorem too. And the second one is about the average acceptance rate bias or variations. Still, it is bounded by the what do you call the weighted sum of the residual mass, but somehow it shows that it's not quite a tight bound, which is less satisfying. By the way, but still, you can see that the number is the gap is very small. I mean, it depends on how you define it, because 0.08 or 0.06 could be relatively small, I guess. So this is just a recap of our main contribution. We have this idea that we apply speculative decoding to federated LLM inference, so that each worker can verify these draft tokens in parallel for inference acceleration. And then in a distributed manner, we saw that we find out that the communication bottleneck becomes a very significant problem, and then we choose as our compression ideas, that is top K, very naive ideas, but we do provide a very solid, some of the solid proofs of our theorems for our proposed two reconstructing methods. Yeah, over here. And then in our evidence, we show that the small distribution level bias under strong compression across temperatures. This provides some of the more or less practicabilities in our system. And some of the open questions for discussion. Also, this is some of the downside of our work. That is, please be attention. This is just to make sure to provide in theory. Our work is just provide in theory that federated LLM is a viable solution, but doesn't necessarily outperform a single large language model in inference. So we need to choose your models, choose your weights very carefully, depends on your task, because each of the mission or task could vary a lot. If you do like text generation, you probably get a good one. If you do coding mission or coding tasks, probably you get a less satisfying solution results. And the second one is that we simply assume the K to be the same for each of the worker, but K should be adapted according to the workers, according to the temperatures, or even according to the tokens. The second one is the third one, last one. I think is very important. Is that we assume that all of the workers share the same token either, which means they have the same vocabulary, but in the practical system, normally you don't have. For instance, you have a llama model, you have a queen model. Then how does these two models work together? So that's pretty much all for my talk today. Thanks. If you have any questions, I guess.
Thank you very much for the speaker. We welcome any questions. If you have any questions, please raise your hand. Yeah, maybe I have one question. So
yeah, please go ahead.
Yeah, you introduced a very promising direction, but what are some potential applications for this federated speculative decoding?
That's very good one. The first one, I guess, is that we try to make sure that the symbiosis of different models. For instance, you have like the models from Meta, you have models from Alibaba, you have Llama, you have Queen. How does them work together, right? The second one is that all of the models they may deployed into different devices or different workers. How to make sure them work together in a harmonized way. This is one of the solutions, I guess. Yeah.
Yeah. Thank you very much.
Thank you.
So if there's no more questions, I guess this will be the end of our workshop. Thank you everyone for attending our workshop. yeah, let's enjoy the rest of your day. Thank you.
Thank you.